welcome to the Data on Kubernetes session. I'm super excited to talk to you about this topic, so let's get started. My name is Akshay. I'm a product manager in Google Kubernetes Engine, GKE. I focus on data and storage integrations just to make our customers' lives easier. I'm joined today by Prasanth, Veerina, who will come up on stage later. And he's the founder of this pretty cool startup called pixelcut.ai. For today's session, we're going to first take a look at the evolution of data on Kubernetes, just a little bit of context on how we're listening to customers' needs. Because Kubernetes is a general purpose data orchestrator, so we're actually adapting it based on what customers are asking us. Then we'll, of course, AI/ML is everywhere. We'll take a deep dive into what are the needs customers are sharing with us on AI/ML training and some potential solutions we have. Same case with AI/ML inference or serving. And then we'll take a look, and Prasanth will come up on stage, and you'll take a look at how he's been able to implement it at Pixelcut and drive value with some of the solutions to his customers. So typically, data on Kubernetes has been really popular with stateless applications. These are ephemeral applications that are request response based. But over time, we've seen customers use and run data on Kubernetes in terms of the stateful apps. It could be your Kafkas of the world. And even if you look at some of the newer apps like vector databases, they're being run as well on Kubernetes. So Kubernetes moved from the stateless world to quite a stateful world, and stateful applications are a real deal now, as you'll see in some of the data shared later. And then, of course, we are now entering a new phase, as all of us who like to build new technology. There's some unsolved problems coming up with data and AI/ML, which we'll explore. So that, just for storytelling, I'm just calling it as DOK 2.0, because the evolution is happening as we speak. Very brief here, pre-DOK, Kubernetes was very focused on ephemeral applications. And the most data applications you saw was mostly were ETL and batch. And there was I think the key takeaway was the community was very hesitant to recommend Kubernetes for database applications. And what we eventually saw was we asked customers why, and there were two reasons. One is they didn't have enough safety features in terms of data orchestrations, things like backup, HA, Kubernetes upgrades. Those were something that really concerned them when it comes to data. So we built a bunch of features like backup for GKE, stateful HA. We have like upgrades that is very aware of stateful applications. And then, of course, they also wanted storage integrations. That was essentially a layer which we also built upon with integrations with the CSI, which is the container storage interface, with block, file, object, and all of the different storage selection customers would need to run stateful applications. And then what we've seen is the proof's in the pudding, like the investments are bearing fruit. We've seen two data points here, one qualitative and one quantitative. The qualitative data is actually more interesting to me. There's a data on Kubernetes community, which is adjacent to the CNCF, and they ran a survey with the CNCF community. And over 40% of leaders said, hey, we're not only running data on applications on Kubernetes, but we're also being more productive. And our productivity is improved by twofold. And we asked some of these customers, why are you more productive? And it boiled down to two reasons. One is, obviously, you have economies of scale in your infrastructure where you're running your stateless and your stateful and your data apps in one stack. And two is familiarity in training. They could train their personnel with Kubernetes, and that kind of scaled across both apps. And then the quantitative data here is, since 2019, the number of clusters running data and stateful apps on GKE has doubled every year. As you know, as numbers grow, it's harder to sustain the growth rate. But we're being able to sustain it because we've really invested in making Kubernetes safe for stateful applications, and this has happened already. So now let's get on to the more exciting part. Like the AI/ML is a big deal. So we essentially are in this new wave where we're hearing new problems from customers on data for AI/ML. And we'll split this up for training and for inference. Training is usually for data sets, and inference is usually for the container image, which is the inference server, and the actual model weights, which we'll take a look at next. Let's start with training. Let's take a look at data for AI/ML training and what are customers telling us. So the problem statement here is actually quite simple. Customers, when you ask them, especially the AI/ML customers, what is your storage choice? I think cloud storage, which is Google Cloud's object storage, is very popular. And why is it popular? It's extremely cost efficient, it's scalable, it has integrations with Python through the SDK, and I can't emphasize how important that is to have integrations with Python. So it's almost the default storage for customers to use for AI/ML-based applications. And it works great. Like a lot of customers use it and with the SDK for training. But what has happened with all the way the training data is changing is the shape of the data is changing. And there happens to be a lot of small files. For example, with driverless car training, there's a lot of small images, which is less than like they're a few megabytes in size. And there are 100,000 plus of those. So what customers are telling us is, look, we love to have our data in GCS, but we need some sort of caching mechanism because going round trip to GCS for every single file is adding a bunch of latencies. And this comes up in 3 symptoms. The first is they are finding it hard to drive the GPU utilization up because data is being a bottleneck. And a lot of our customers are running expensive accelerators like GPUs and TPUs. And the last thing you want is your data to be a bottleneck to not drive up high utilization. And then the second and the third is symptoms we see is actually really important as well, is customers don't want to be storage experts. They just want their storage to be GCS and a lot of the caching to be automatic by GCP. Instead of them having to learn about a bunch of storage and move data around, it's quite painful. And if you think of all the decisions customers have to make when they're running training jobs, they need to select their accelerator, they need to select their framework. There's so many decisions to make. By the time they come to storage, they face decision fatigue. And they really want a simple and opinionated solution to work with GCS. And some sort of managed Google solution for caching like small data such that they don't have to make the round trips all the time. So sometime in the mid of last year, so mid-2023, we launched GCS Cloud Storage Fuse. It's been super popular because one is it's also very portable. It's Python native. Like if you look at the Python code, how you load data sets, it's super easy to just specify a file path because it's Fuse-based. It supports file semantics. And it's also a vehicle for us to pass on as infra people. We want to help our customers. So it allows us to pass on infra optimizations to our customers over time while you keep your data in the same familiar place, which is GCS. So one such optimization is we reduce your resource idle time. For example, if you're using the SDK, you have to wait for your data to download. But with Fuse, data is automatically streamed, so your training can immediately kick off. And of course, Fuse has been around for a while. You may ask, OK, what's the big deal? I think there was a lot of stability issues with it. So we invested a lot in Google to make it really stable over time. And the proof's in the pudding here with customers. We have a pretty good adoption of the Fuse CSI on GKE. Customers like Equifax using it for a Jupyter notebook use case. We have customers like OpenX using it for AI/ML ad tech training. And then we also have customers iterating over a lot of protein files with Reveal Biosciences. So Fuse is out there. It's been out since last year. But the thing is, it didn't support caching and automatic read caching. So if you had a lot of small files, you had to continuously make the round trips to GCS and back. And that hurt training times. Customers, they didn't want to keep going to make those round trips to GCS and back. And that's why today we're launching Cloud Storage Fuse CSI with read caching. So your data stays in the same familiar place, which is GCS. You have portable file semantics that is very familiar to the Python developer. You just have to change your file path to access your data. And now your data is cached on your local storage. So what does this mean is if you're accessing data over and over again, you essentially have up to 3x higher throughput for your second epoch onwards, because after the first round trip, we cache the data locally. And as your training job undergoes multiple epochs, since from the second epoch the data is cached, you observe a lot of benefits in terms of training types, based on our benchmarks up to 57% faster training times. And because you're feeding the beast here is the GPU or the TPU, which is a hungry accelerator, you're actually increasing its utilization and saving on training times. I'm actually going to switch to a quick demo where you'll see this in action. So here, I'm just creating a GKE cluster with a local SSD. Local SSDs are important because it's high performant for your storage. It's a local storage, and it's provisioned on the GKE node. I'm uploading the training data to GCS. So here's your training data in your familiar GCS location. You have your training data. Then in your GKE pod, all I do is enable Cloud Storage Fuse. I make sure I have my local SSD enabled. We're running DLIO here just to simulate the benchmarking in terms of the training loop. And then this is the really fun part of GCS is, or the Fuse interface is, your data stays in GCS. So all you have to tell us is where your data stays in terms of your bucket. And then this is the feature we launched today, is where you can actually specify a file cache. So you essentially will ask GCS Fuse to cache data locally after your first round trip of fetching your data from GCS. And that's it. So you just run the pod. It's super simple. DLIO is starting to run just to run through many training epochs to simulate the training loops. And then you see that based on some of our results, we're seeing the GPU utilization improve, as well as your overall throughput improve, because now on every from your second epoch onwards, you're reading it from local storage. So we took a look at Cloud Storage Fuse and how we enhanced it with read caching, just to ensure that we're working backwards from customers' problems of improving GPU utilization and data not to be a bottleneck. But we also heard from other customers, specifically customers in the HPC community, who are also very active in AI/ML as well, who are very used to parallel file systems. And parallel file systems is a very popular high-performance storage option on premises. So sometime last year, specifically at Google Next last year, Google launched a first-party parallel file system called Parallel Store. So what we've done with GKE is we have provisioned, we now have a CSI driver with Parallel Store in private preview. What this means is you can provision Parallel Store with the CSI semantics, which is Container Storage Interface. So you get the Kubernetes native way of accessing Parallel Store. But we didn't just stop there. We asked customers, we really work backwards from the training user journey of data is in cloud storage, and Parallel Store is a drop-in accelerator. So we built features in Parallel Store and GKE to support out-of-the-box data transfer. So you can tell us, hey, my data is in cloud storage, accelerate it with Parallel Store. We will transfer data all the way from cloud storage to Parallel Store. And when your pod runs, the data will be hydrated from cloud storage, and it can easily run and start its training loops. And this, of course, because you're running on a very high-performance storage options, you also get faster training times, which is working backwards from that same problem of feeding the beast. We have a quick demo now, which I'm going to switch to kind of show you how Parallel Store works. So as I said, we're going to, for this demo, we're going to fine-tune BERT, which is Google's OSS language model. And what we're going to do is the training data sets on GCS. Most of our customers have it there. So we introduced a new custom resource definition in GKE called a GCP data source. And that's for you to tell us where your data resides. So here we just, in this demo, we said, hey, my data is in cloud storage, and here's the URI. That's all you need to tell us. And then when you're creating a volume, a Kubernetes volume using your familiar CSI, you essentially then just pass the data source, or the GCP data source, as a reference to your PVC, or your persistent volume claims. And that's it. GKE will kind of work behind the scenes to kind of transfer the data from cloud storage to parallel storage, so you don't have to do that heavy lifting of moving data across silos. Now, once the volume is provisioned, we will then see that the PVC is created successfully, and all the objects have been copied from or hydrated from cloud storage to parallel store. And then, of course, the last part is then actually running the training job itself, which is a Python program. So we have the YAML here on the spec. And what you'll see here is the volume is mounted, and parallel store CSI will be the provisioner. And the fun part here also is it's mounted at /data path, so the pod can access it. And in the Python layer, this is why it's also really important, is all you have to ask your data scientist is just change the path. And that's pretty much it. The job is complete. It actually loads the data, it trains it, and we check the log to see that the data set was loaded and the model is fine-tuned successfully. So you saw the parallel store GKE CSI integration with built-in GCS hydration. So to summarize, we took a look at how you can actually store your data in where customers want to store data, which is cloud storage, where it's very familiar for them. We also showed how we have out-of-the-box integrations with for caching your data with Cloud Storage Fuse and Parallel Store. Both of these help accelerate your training times because of the way they cache data, and it's really important, especially if you have training data that has a lot of small files. And then the third is also most important, is they are made accessible through a very easy-to-use file semantics pattern, which is very portable with how the Python community embraces data access patterns. So it's very portable and easy to use. Cloud Storage Fuse read caching is generally available with full Terraform support across both GKE, standard, and autopilot. So if your use case is more eminent, it's something you can use today. With Cloud Storage Fuse, your data is cached locally on the node. A parallel store is in private preview, so if your use case is more imminent, we'd obviously recommend using Cloud Storage Fuse. The parallel store will obviously be GA soon as well, and that is where the storage is more decoupled from your node, and it's slightly higher performance, as you can see in some of the numbers here. So we took a look at AI/ML training. We took a look at how you can use storage options to accelerate your training. Let's take a look at AI/ML inference as well. So we asked customers, okay, what are your key pain points with AI/ML inference? I think here too there are like data loading problems. And the data loading problems here is slightly unique in that it comes to two separate data sources. The first is customers have very large container images. If you take a look at some of the popular inference servers like NVIDIA Triton or SaxML, they tend to be tens of gigabytes. And loading these essentially from 0 to 1 or 1 to n actually introduces a large latency in terms of some sort of a cold start, which is actually painful for most of our customers. If you think of inference, the name of the game is to minimize your cost per token. So it is a big pain point for customers in loading large images. And then once the model weights are, the container image inference server is actually booted up and then the process starts, usually there's a process where it actually loads the model weights. The model weights is usually stored in object storage, like Google Cloud Storage. And that can be up to hundreds of gigabytes large. So it is something which also adds latency to the overall process. And then just to give you an example, we took Llama 270B, and the container image has a bunch of layers baked into it. So it's pretty big. It's around 16 gigabytes. So, and then once that container actually starts up, it actually needs to load the model weights, which is another 140 gigabytes. So it's essentially an assembly line where you're adding on latency, and there are a lot of solutions customers are looking for to speed things up. That's a little bit of the workflow, of most of which I spoke about, but the second and the third step is important, where the image is pulled, the container starts up, and then it actually loads the model weights, which are then loaded into your GPU memory, and then you start serving requests. So the green and the pink ones are like adds latency specifically to what we're talking about right now. So we're introducing GKE container preloading for fast acceleration of container images. This is essentially to speed up your loading of your inference server container images. And how we're doing this is we're using the concept of a boot disk, and we've introduced something called secondary boot disks. Boot disks are fun storage that comes out of the box with every node, where you can kind of bake boilerplate bits which is needed by your applications. This is now available for you to use. The user journey is quite simple. All you need to do is you need to tell us where your container image is, whether it's an artifact registry or Docker Hub. And then we create a disk image out of it, which is essentially a PD, a persistent disk-based image, which essentially goes into the boot disk. And then you would create your node pools and say, hey, create a node pool with a secondary boot disk and with this disk image, which essentially references a container image. And then when your workloads are scheduled, you get that automatic acceleration out of the box, and you don't pay for that download of the container image from any sort of registry anymore, because now it's all baked into your node pool through this feature. The other features we're launching today is also to accelerate. We took a look at the acceleration of the container image. We also learned from customers they want to accelerate their model weights. GCS Fuse has already been GA. It has been, as I said, since mid last year. You can actually use GCS Fuse to load model weights faster than the SDK. The blue line here is FSSpec. FSSpec is what the SDK uses underneath the hood. Because GCS Fuse downloads the data, essentially dynamically pulls the data, your application doesn't need to wait for all the weights to download, and that's why it has faster results relative to the baseline, which is the SDK. And we're also introducing PDSSD. PDSSD has already been around, but we're also introducing hyperdisk ML, which is the newer, more modern block storage offerings from Google Cloud. And those can be used in a read-only many pattern. So you can load your model weights into something like a PDSSD, and Prasanth will be talking about it as well in his talk and how he's been able to use that pattern and accelerate load times at pixel cut. But yeah, that's another pattern which we see customers use. So these are the two techniques you can use together to accelerate your times. Some of the results and benchmarking we did with some common models like Gecko, Bison, and Llama 2. And we've come up with some recommendations as well. If your model size isn't that large, the model weights, I should say, you can use GCS Fuse, the easiest way. It's super portable. Your data is on cloud storage. You don't have to think about read-only many PDs. It's a lot easier to use. But if your data size is larger, you may want to consider something like a PD-based solution, including hyperdisk ML, and I think 20 gigabytes is one way to think about it, based on our benchmarks. But it really depends on your use case and how much you're willing to tolerate in manually orchestrating data versus getting something like more simple like GCS Fuse versus Cloud Hyperdisk. And one thing which I want to highlight is these launches are very complementary. You can use your container, your secondary boot disk and container preloading to accelerate your loading of your container images, which usually have your inference servers like Triton or SaxML. And then you can attach like GCS Fuse to download your model weights, or PD-based read-only many patterns with either PDSSD or hyperdisk ML. Both of them it's really complementary, and this is how we're thinking and positioning this for customers, and we hope that that will be the way customers consume this pattern. So we took a look at training and inference and some sort of data on Kubernetes evolution. I'm going to call on Prasanth to show how they actually, PixelCut use some of these features to drive value for his customers.
Cool. Thanks, Akshay. Hi, everybody. My name is Prasanth Veerina. I'm co-founder of PixelCut. Really excited to be here to tell you about how we implemented some of these best practices to improve our ML deployments on Kubernetes. The work I'm going to be talking about was done by a team member of ours, Purva Shah, so shout out to him. Cool. So at PixelCut, our mission is to give every merchant creative superpowers. We build tools that enable small businesses and online sellers to create professional-looking imagery without having to go to a photo studio or hire a photographer. So you can see in this example, a merchant can just take out their phone, snap a photo of their product, and then edit it using our tools. And in this example, you can't quite see with the contrast there, but the background's been removed, and we've cast a nice soft shadow. That shadow is completely generated using one of our generative AI models. And so customers are using PixelCut to process millions of images every single day, and all this inferencing is happening on GKE. So let's talk about one of the challenges when it comes to deploying your ML inferencing on GKE, and that's auto-scaling. As I mentioned, customers use PixelCut to edit their images using our generative AI models, and we need to be able to scale those models up and down responsively according to demand, right? So time of day, burst of traffic, this sort of thing. Additionally, in order to manage costs, we make heavy use of spot instances. And so if you're using spot instances, I'm sure you're familiar, they can sort of pop in and out at any time. And so you need to be able to start up your new containers pretty quickly in order to be robust to that sort of turnover. And so in our case, this sort of gets to the crux of the problem, which Akshay already mentioned, which is that these ML containers can get pretty bloated. So we had one container which was over 19 gigabytes, and we were facing pull times that could sometimes exceed 30 minutes if you're facing sort of image pull errors or network issues. And even in a good case, it would take up to 6 minutes, which obviously isn't great for responsiveness. So ultimately, this all leads to a poor customer experience, right? If you can't scale up effectively, you're dropping requests, your customers are seeing increased latencies, and as a business, you have to constantly be over-provisioned in order to meet demand. And so that obviously impacts your bottom line. So we sort of came to Akshay and team with, what are the best practices to address these issues earlier this year. And we found that there's sort of 3 really simple but effective solutions that you can use to tackle this problem. So the first is to simply reduce the size of your container image. This is a best practice that is sort of common for any kind of deployment, but you'll find in a lot of these ML containers, there's a lot of cruft in them. So if you're careful about choosing the right base image, optimizing your layers carefully, and stripping out any unnecessary dependencies, you'll probably be able to get some gains there like we did. In step 2, we implemented the solution that Akshay talked about in terms of offloading some of the heavy dependencies and model weights into a PD SSD. So that SSD is then mounted as a read-only many volume onto our ML pods as they come up. And so we can just read some of our heavier dependencies and model weights without having to package them into the container itself. With steps 1 and 2, we were able to reduce our container size from 19 gigabytes to around 4 gigs. So that's obviously a big improvement. But we actually get a secondary benefit where after the container is started up, we don't have to wait and pull our weights from GCS. We can just load them directly from the volume, which is a lot faster. So finally, in terms of step 3, we enabled some of these new features that Akshay's been mentioned, including secondary boot disk and image streaming. So these features, image streaming has been around for a little bit, but secondary boot disk is sort of a more managed way to do step 2. So I highly recommend that. If you're going to try this at home, I actually recommend going straight to step 3. It's really quick time to value. These features are sort of flag flips that you can do on your Kubernetes cluster, so really easy to test out and see if you get acceleration there. So let's talk about results. As you can see, a really massive improvement in our image pull times. So we had sort of a 6-minute baseline pull time that I already mentioned. When we offloaded all of our weights and we thinned our container image, we got down to around 60 seconds. And then once we enabled image streaming on top of that, our pull times now look like around 2 seconds in a typical case. So that's pretty incredible. We went from pull times which could take tens of minutes in some scenarios to just seconds. We largely eliminated our sort of failure scenarios, and this has obviously had a material impact on our business. We're able to run with far tighter provisioning, be much more responsive to scale up and down according to demand, and ultimately deliver that great customer experience. So if you want to support a startup, you can check out our website, pixelcut.ai, and with that, I'll turn it back to Akshay, and I think we have some time for questions, so I'll just stay up here. Thanks.